Hello, my name is Ali.
Hi, my name is Ankita.
Hi, my name is Seth Wardlaw. We are from the STEM Early College, which employs a real-world and problem-based method to help students develop critical and unique thinking skills. STEM focuses on understanding the engineering design process and being able to test different designs and methods. Our project is an example of this. We are here to present our senior internship project, a project in which we work closely with a mentor in our field of interest and produce something new.
We work with Dr. McCullough, a professor in chemical, biological, and bioengineering at NCA&T. Dr. McCullough is in charge of a research group that focuses on bioengineering, with many of the students modeling different parts of the body or medical devices. We participated in this as well as sought to create a medical device known as a Nuss bar for the disease Pectus Excavatum.
Pectus excavatum is a condition in which the chest is sunken due to a damaged sternum. In this condition, there is an extra pressure placed on the internal organs, such as the heart, the lungs, and the ribs. And since the sternum is sunken, there's no protection to those significant organs. In order to fix Pectus excavatum, an arched metal bar is inserted in between the ribs, which is used to push the sternum outwards. This is called a Nuss bar, and it has the issue of not being able to account for the growth of the ribs, as well as being affected by the increasing pressure of that growth. Due to this, the procedure is usually very invasive and is done multiple times over the course of a patient's lifetime to be replaced as the patient is growing.
So for our design of the Nuss bar, we wanted to create a bar that could grow with the patient so that the surgery would not have to be done multiple times. Because our goal was to create a bar that would grow with the patient, we decided to have a telescoping bar that could be extended to accommodate that growth. This would remove the need for the consistent removal and implementation of the bar over and over again.
Our redesigned Nuss bar aims to be extendable within the body. To achieve this, it will be robotically extendable so that excessive surgeries are no longer a factor. The telescoping allows for a minimum length of the sternum size at the start of the procedure and a maximum growth of up to 9 inches. This is enough to accommodate the growth up to an adult without having to redo the original Nuss bar procedure. A robotic extension allows for the bar to be easily extendable within the body.
To effectively do this project, we had 3 main objectives when we were trying to come up with an idea. And those were designing the blueprints, 3D modeling our design in some kind of software, and finally coming up with like a complete product that shows everything that we wanted for the bar. So the first thing that we did was that we drew out multiple sketches of our redesigned Nuss bar. We each came up with our own design, and then we worked together to create multiple designs as well. So to get the general arc, like the arch shape, and understand how deeply we needed to be arched. And then second, we drafted out the sketches along with the extendable edges. So we started with 2 main designs, an accordion extension and a telescoping extension. So the accordion extension is made up of a singular bar, but both ends have a zigzagged end to compress and decompress as we needed it to be. And then the telescoping extension has a static middle section that does not move, and then multiple bars that fit into each other in order to be able to compress and be pulled out.
We originally had qualms about how to externally extend these sections as we were first contemplating heat, but after further researching the effect of external modifications like temperature and electronics, we decided that the accordion method might not be strong enough to actually hold up against those specific factors along with the pressure of the sternum. Finally, we decided on a telescoping method as the ideal design. We decided to use a nickel and titanium alloy called nitinol for the material of the bar. Nitinol is one of the most flexible metals that would still be able to bear the minimum of 300 Newton loads of the sternum. And it's also a medical grade material. It's often used in dentistry and cardiac stents because it resists corrosion, has a good flexibility due to its Young modulus, and is a very biocompatible metal. This means that it won't cause any medical harm to the organs or cells around it.
In order to test the effectiveness of the bar, we modeled a 3-dimensional structure to determine any possible limitations. Based on the model, we we made adjustments and figured out the rough dimensions of the bar, and determined that the middle would be approximately 2 inches long, so that the shortest length of the bar would be 9 inches, and the bar would be able to extend up to 17 inches in total. With such a large range, this would allow the patient to be able to avoid surgery from childhood to adulthood, at which point the Pectus Excavatum condition would be cured for the most part. In order to be minimally invasive, the bar should be able to extend externally, which is why we decided to use a robotic Nuss bar. Adding the feature of the robotic extension allows for an external growth method to eliminate any additional procedures. The extension would be done as needed during checkups.
Our main goals for the bar that we really needed to be accomplished were that the bar would be able to be used for any patient, meaning that the bar would be able to be modified to fit any individual. So we accomplished this by the range in length that our bar could accommodate. Although we decided on a 9-inch to 17-inch range, the bar's simple structure allows it to be made smaller or bigger as necessary. Also, we wanted the bar to be able to hold up over a long period of time rather than collapsing under a heavy load like of the ribs or the sternum. For this reason, we did significant research on some of the stronger metals that the body could accept, and we decided on nitinol and nickel with the 1-on-1 ratio, and that would be the best fit for the conditions, and that would be able to hold up the load as well as be flexible enough to accommodate any patient.
This is a 3D rendering of our final Nuss bar design. As you can see, the overall bar is slightly arched, since the bar should be able to put enough pressure on the sternum in order to push it outwards. This model shows what the bar would look like when it's fully extended. The ends are able to be pushed inwards, allowing the bar to be varied in length. Our next steps would be modeling our design within a program called SolidWorks. This would allow us to animate the extension and understand what might be a nuisance factor in the design. We know that nitinol can hold up to 300 newtons, as well as its Young modulus being a high enough number that it has an ideal flexibility for the arching of the project. However, we have to be able to test the load of the 300 newtons to actually see how that pressure would affect the structure and possible degradation of the material over time. SolidWorks allows us to do both of those things.
We would also have a physical prototype of this bar and have it 3D printed or produced. Possibly, in the future, our bar would be a part of clinical trials as well as becoming an active member in the medical field.
Thank you for your time. You can contact any of us if you need to, if you have any questions, through any of these emails. And these are our works cited.